Okay, thanks for coming. Today we will continue the introduction of the associated points. And so we will prove some several property of associated points on affine scheme. And then we will try to generalize it on general non-affine schemes. So to be honest, I skipped this session when I first read, so I hope what I say will be at least correct. So let's begin by recording what is associated points. So at first we will only look at affine schemes. So spec A, where A is Noetherian, and then we will look at the finality generated A modular M. And in case you know, the definition we're using here, which is the definition we discussed in the last talk, is actually a first property A. So in the later of the session, we will give an algebraic version of the definition, but this property is somehow characterized the associated point. So now we are using this as a definition. So the definition does the associated points are the generic points of irreducible components of support M for M in M. So support M is the ideal that MP is not equal to 0. So remember last time we talked about that example about the KSY, XY, Y square, and then one generic point will be this with Y, and the another one is the XY. So to be honest, I always feel a little bit confused about this definition at the beginning. So right now I will talk a little bit about the algebraic version of this story. So what is the support of M? So you can see that P is in support of M only if MP is not equal to 0, which means for any A not in P, A
for
M.
any, or it exists?
I mean for any. For any A not in P, AM is not equal to 0. So if you remember the notation of annihilators, so annihilator AM is just all the elements in A that AM equal to 0. Then this means that everything not in P will not annihilate M. So in other words, the annihilator of M is in P. So what does this mean? This means that the support M is just the closed set of annihilator of M. And I find this a little bit easier to do the computation. And so if this is a support, and what is the generic point? What's the generic point of its irreducible components? They're just the minimal bright ideal containing this set. And unfortunately, this is not the exact same as the algebraic definition we gave later. And I think they're actually the same thing, essentially the same thing. But we'll take care of that later, maybe in the next talk. So forgive me to use this little bit ugly notation. So we will call associated points of M over A like this. So here is a property B. for a fixed M, this set is finite. So again, by the structure of the Gibbs node, there are several of this property, A, B, C, D. We will not prove now. So we'll prove that later. But in this talk, we will more focus on what property we can see starting from these things. So we can see, right now we can just see as something as accident that we take for granted. So, so just that. For fixed M, there are only finitely many associated points. So here's another property we'll actually prove. So we will prove that this map is injective. So what I mean by this map? So if you remember that when we define the structural shift of a scheme, at that time we also proved that if you have an A modular M, then in spec A you have a shift M that is defined by spec A equals to M, and for distinguished open subset, the localization. So in that time, we proved that this is actually a scheme. So if it's a scheme, we already know that for all the P, for all the prime ideals, this will be injective. Because shift is determined by all the stock. But this means that you do not look at all the stock. You only need to look at the stock where it is associated points. And this shift will be determined by these stocks. So the proof of this is easy. So if M you map to 0, so if AVMP is 0 for all P, so what MP equal to 0 means? That means P is not in the support of M, not in support of M. So if all MP is 0, that means the support M contains no associated point. But that would mean support M is just empty. Otherwise, if support M is not empty, you must have associated points in it. If it's not 0, you must have associated point in it. So if all associated points are not in support M, that means the support M is empty. That means the M is supported nowhere. So from this map, we know that everything in here is 0, so that M is 0. So M is 0. So all MP equal to 0. That means M is 0. Okay, the next one. The next property will give another characterization of the support M. So say that support M is M equals to union So this is actually just another way to look at the definition. the support M is the closure of all the union of associated point that has non-zero non-zero June. So, so first thing we can see that since we know that the set of associated points are finite, this is finite union, and the union and the closure can commute. So this is actually the union of closures. So to prove this is also easy for any point, for any prime ideal, for any associated point that has MP not equal to 0, we automatically know that it's in support of M. P is in support of M. So this side will be a subset of that side. On the other hand, we know that the support M is a closed set that can be written as a union of irreducible components. Irreducible. And each reducible component is the closure of a generic point, which is associated point. And those associated points also have non-zero Junes. So that we know that this side is on that side. So this union will be in that bigger union. The next property. The next property will be about the non-reducedness of the scheme. So again, I'm using another Algebraic notation. N is equal to order spec A that AP is non-reduced. So this set is all the non-reduced point in the scheme. And we want to show that So we want to show that if you look at, you want to find all the non-reduced points on the scheme, you only need to look at the non-reduced associated point, and then you take the closure of them and the union. And well, that's the same. The union of closure, the closure of the union is the same because the associated points are finite. So that means that this associated point, this non-reduced associated points will take the brane of all the non-reducedness of the scheme. So the proof, actually we'll start from this side. So first, for this side, we need to prove that if P is in here, if P is in associated point and non-reduced, then everything in this closure is also non-reduced. That's this side. So if Q is a point in this closure, that is the same thing to say that P is a subset. Wait, is it? Yeah, P is a subset of Q. So if you look at these two sets, this is the localization on A minus P, and that is on, I will say QP. QP. So AQ is a localization on A minus Q, and AP is a localization on A minus P. If P is a subset of Q, then A minus Q is a subset of A minus P. Then this is just a localization. This is a localization. From a smaller set to a bigger set. And then localization preserve reducedness. So if AQ reduced, then AP is also reduced. So I don't think we have proved this before, right? Localization preserve reducedness. So so here I just give a short proof. If A is reduced, but S inverse A naught, then so here's bracket. Then that means some AX to the n is equal to 0, but AX is not equal to 0. And that means for T in S, T A to the n equal to 0. But that just means T A to the power is n is also 0. Then, by the reducedness of A, we know that TA is 0. And TA is 0 means that this is also 0. That's a contradiction. So this is proof for this statement, localization preserve reducedness. So if AQ is reduced, then AP is also reduced. We have assumed that P is non-reduced. So everything in the closure of P is also non-reduced. And then for the other direction, if AQ non-reduced, let's just say this. If AQ non-reduced, we want to find a P in associated points that is also non-reduced, such that Q is in P. So again, AQ is if AQ is non-reduced, means that there is this. I use another notation here. Fx equal to 0, but Fs is not equal to 0. And again, this means T Fn, this means exists A not in Q, such that AFN is equal to 0. And this means for any not in Q, BF not equal to 0. And then AFN equal to 0 means that ANFN equal to 0. If we write G as AF, then this means that G to the power of N is equal to 0. The next step will be, but we know that from this statement, we know that G itself is not 0. Because G is AF, and anything like this is not 0. So now what this means? This should mean that Q is in support of G. Yeah. So this will come from this statement. For anything that is not in Q, BF is not in 0. That basically means that for anything that is not in Q, CG is also non-zero. Because CG is CAF, there is something not in Q multiplied by F. So we know that Q is in support of G. But if it's in support of G, then for some reducible component of this support, and there will be a if it's in support of G, then it's in some of the reducible component of this support, and it is also in closure of some associated point. So this means Q is in some closure of associated point. Here P is in support of G and associated points. And then don't forget that we also need to prove that P is non-reduced. AP is not non-reduced. So AP is non-reduced because of G. So I want to say that G is not 0 in AP. That is because P is in support of G. And then G to the power N is 0 in A, then 0 is also 0 in AP. So that means AP is non-reduced. Okay, so this will finish that proof. Now we can also look at the example we see before. In the KSY, SY, y square. Here we have two associated points, y and sy. And you can see that the start at y is reduced, but the start at sy is not reduced. So we immediately knows that the only point that is non-reduced is in the closure of this point, which is just this point. Okay? And here is another property we're not going to prove right now, C. And element F is a zero divisor of M. That means there exists some M, Fm is 0. If and only if F vanish at some if only if f1 is at some associated points. So remember, if f is a zero divisor of M, that means f is in the numerator of that element M. And it's also in some of the associated points that contain this. So that's this direction from this to this. And this probably shows so that the other side is also true. So I think right now I'm not totally sure, but I think this statement is the connection between the definition we use at the beginning and the algebraic definition we use later. So here is another important exercise, important property. It says that the definition of associated point and well-behaved under localization. So, so this property says that if associated point, so I just write it as this form. Associated point of S inverse M. So here X is a set in A that's closed under multiplication. So the associated point of S inverse M is the same thing as the associated point of M that is also located at S inverse A. So basically you have A, you have a spec A, and the localization of A on X is a subset of this scheme. And we want to say that the associated point of S inverse M are those associated points of M that is in this subset. And this will be the most difficult proof of this talk. So first we can see that associated point of S inverse M are just the prior ideal, that minimal prior ideal containing something like this, MX. This other minimal prior ideal containing the associated point of this are all the minimal prior ideals containing all the numerator of everything that looks like M over S. And the associated point of M are just all the minimal prior ideal containing a numerator of M. So we want to show that the minimal prior ideal containing this are the minimal prior ideal containing this, but also in this subspace. And remember, P is in spec S inverse A if only if P do not intersect with S. So first we show that if P So first we prove one side of that containment. If P is a associated point, so here is any prior ideal containing this enumerator, and P do not intersect with S. Then we'll say that P is also in the support of this MS. So here, if not, then P is not in the support of MS. So actually here, the S doesn't matter. So don't worry about which S we pick. If otherwise P is not in the support of MX, that means MX P is equal to 0 in S inverse MP. Here we have to take care because there are two localizations here. So this means that exists A not in P such that AMX is equal to 0 in S inverse M. And that means there exists T that is in X such that AT M is 0. This is just in M. And that means AT is in a numerator of M. And remember, we assume that P contains this numerator. So A is not in P. T is in X, but S do not intersect with P. So both A and T are not in P. But the product is in P. So that's a contradiction. So this will show that the one side of the containment, everything is in here. The minimum, any prior ideal in here is also a primary ideal in here. So the minimum one in here is also the minimum one in here. For the other side, for the other direction, we need to prove that all the minimal prior ideals containing So now we are really using this minimal here. The minimal prior ideal containing the enumerator of MX are the minimal prior ideal containing enumerator of M. That doesn't mean S. So here we will look at the AP. Look at AP. So this is just the localization map, and then P will be mapped to the P P. So we want to say that if P is the minimal prior ideal containing this, then the localization PP is the minimal prior ideal containing this. So why is this true? This actually comes from a statement we proved a long time ago about that the Zariski topology on the spec AP is the induced subspace topology on spec A. So anything in here containing this will correspond to anything in here containing this. So the minimal one containing this set is the minimal one in here containing this set. And so P is the minimal containing SP. So what this means? It means that if you look at this set, so remember, PP is the maximal idea in AP. It's also the minimal one containing this. So that means P is the only prior ideal between these two sets. So that means P is the has only one prime. That is the P. So if it is the only prior ideal, it is also neurotical. And where? And there's another thing I need here. That is the localization commute with the taking quotient. If you can't remember why this is true, you can just look any book, any commutative algebra book, or just Google it. Anyway, this is true. The localization commute with taking quotient. So PP is the neurotical, means that if this is not true, so if P is a minimal ideal containing that, but it's not the minimal prior ideal containing that doesn't make S, that means T in the set which X is not empty. So I should write this at the beginning, but I forget. So that means there exists some T in P and S. So if P is in P, if T is in P, then T is in this neurotical. That means T to the power of n is 0 in this ring. So that means there exists some A not in P, AT to the M equal to 0 in A in MS. That means A to the T is in the numerator of MX. That means A, T, M, S is 0. Oh, this is so long. And remember, T is an element both in P and S. So if T is in X, that means T is the unit in the AP. But I mean in the S inverse M. So this is 0 in S inverse M. Since t is in x, so t to the power of n is a unit. So this means a t n m t n x is 0. And this is the same thing as a m x as 0. That means a is in the numerator of m s. Which is in P, a contradiction with our assumption. Okay, so this is a proof. Any question? This is a pretty long proof. But remember, Wakil says that in this session, to remember those properties is more important than remember those proofs. So just forget it once you read it, and just remember the result we are proving, the properties. I still have time to talk about the generalization to the non-reduced, to the non-affine. So now with this property that the associated point is well behaved under localization, now we can try to generalize the associated point to the non-affine schemes. So first, associated point can be tracked at any stocks. So in here we know that the localization, the associated point that is in the localization is just the associated point of the localization. So that's what means by it can track as stocks. If you look at the example we're using, remember this is the associated point y, and this is the associated point sy. If you look at the stock at here, the stock at here has two associated points, and one of them corresponds to this associated point, and the other one would correspond to that associated point. But if you look at any point other than that, if you look at a point in here, let's say P is s minus 1 y, then the stock at there has only one associated point. That is correspond to this associated point y. So that is what I mean by the associated point can be tracked as stocks. And now we can define the associated point on non-affine schemes. So here's the definition. On locally Noetherian scheme, he is associated point if so here we're looking at locally Noetherian schemes because we still need the Noetherian condition on the affine, and that P is an associated point if there exists a neighborhood or an affine open neighborhood spec A of P, such that P is an associated point of this spec A. So here you may ask if there are two affine open that containing P, what will happen? So if we have P here and spec A and spec B, then P is so P is in the associated point of A if only if P is in the associated point in AP. So we can look at the localization just at P. Since at that point, P is also in B. So so AP is equal to OXP, which is also equal to BP. So P is associated point at there. It's the same thing as it's the associated point of BP. So this is if only if P is also associated point of B. So this definition is well defined. It do not depend on which neighborhood you choose. Okay, I don't have time to talk another several properties, so we will end here today. And is there any question?